Well, in the last class, I have discussed about the efficacies of using advanced characterization techniques, and I also discussed that why different techniques to be used in combinations. In the subsequent lectures, we are going to discuss about different microstructure related advanced characterization techniques. Microstructure is the basic theme of material science. So, that is why most of the research studies involve not only seeing the microstructure using different kinds of machines, but also to analyze them. So, in this lecture we are mostly going to concentrate on electron microscope, especially the transmission electron microscope. Before I just begin, I must tell you that why the transmission electron microscope is very important and how this technique has been developed over the time period. As you know, electrons are discovered in the beginning of the last century or maybe end of the 19th century, and then people started realizing that electrons can be used for many purposes. But as far as microstructure is concerned, if you want to discuss about microstructure, we should know about microscope. So, first let me discuss about the microscope. What is a microscope? We know that our normal eye can see a feature as small as 0.1 to 0.2 millimeters. So, I can see any feature which is in this range 0.1 to 0.2 millimeters. That means, if there are 2 points on a space, so our normal eye can resolve them very precisely if the distance between these 2 points range from 0.1 to 0.2 millimeters. So, any machine which can resolve 2 points closer than these numbers from 0.1 to 0.2 millimeters can be defined as a microscope. So, therefore, this study of developing those kind of machines began long back. In fact, in 17th century by Leeuwenhoek, first time in the year of 1668, Leeuwenhoek discovered the optical microscope, in which the normal light was used to image many important algae or even small features which are present for the small insects. So, that was the beginning of the microscope, the using of instrument which can resolve objects finer than our eye can do. But it went on for the next subsequent 2 centuries or 3 centuries. The optical microscope was refined and used for many purposes. But in the end of 19th century and the beginning of the 20th century, people started realizing that electrons can also be used for electron microscopes or can be used to image things which can resolve objects much finer than what an optical microscope do. So, this has led to a lot of discoveries in the arena of electron microscope, which I am going to discuss first. Then finally, I go to how the electrons interact with the material. The major discovery which has propelled the discovery of electron microscopy is by de Broglie. De Broglie in the year 1925 de Broglie in France, he first time told electrons can be used as a wave, and he said that electron wavelength can be defined by this formula where h, lambda is the wavelength of the electron, h is the Planck constant, and p is the momentum of the electron. So, therefore, we can write down h equal to this equal to h by m into v, where m the mass of the electron and v is the velocity of the electron. It all started with the discovery by de Broglie in 1925, when he stated that electrons can be considered to be a wave with a wavelength given by this formula lambda equal to h by p, where h is the Planck's constant and p is the momentum of the electron. So, therefore, we can write this is equal to h by mv, where the m is the mass of the electron and v is the velocity. So, by knowing that electrons can be used as a wave or can behave like a wave, one can use this particular feature of electron to make use in microscope. Within just next 7 years, that is in 1932, two scientists, E. Ruska and M. Knoll, first time demonstrated that electrons can be used as a tool for microscope, and first electron microscope, or first rather transmission electron microscope was demonstrated. And this is a major discovery, and for this discovery, in fact, Hans Ruska won Nobel Prize in 1986 after almost 50 years. So, this set the tone that electrons can be used as an imaging tool. People know it because of the fact that electrons can have a very small wavelength. So, let me just state how this history has developed first, then get back into the efficacy of electrons in the microscope. First commercial electron microscope came up in the year of 1936, just after 4 years of first demo of electron microscope. So, this was by a company named Metropolitan Vickers UK, but this microscope was not successful. So, therefore, the first successful commercial microscope came up in the years of 1939, just on the year of Second World War, by Siemens and Halske. But this has basically made electron microscope available even before the Second World War. But then after the Second World War, in those days it was very difficult to prepare samples for TM, because samples needs to be very thin to observe under electron microscope, especially under TM. So, the tool for making those thin foils came up in later on by another German scientist in 1949, just after the Second World War, known as Heidenreich. He discovered the technique to prepare very thin foil so that it can be observed under electron microscope TM. But subsequently, many other companies, not only Siemens and Halske, but many other companies like Geol, Hitachi, even Philips started manufacturing transmission electron microscope, and later on from 1950s to onwards, TM was extensively used to image many samples which is either metallic or ceramic in nature. So, major groups which started working on this research was one in Cambridge, University of Cambridge, and later on in US, United States of America. So, finally, the theories of electron microscope came up by a few scientists in Cambridge, especially Professor Harsh and his co-workers. They developed the theory of TEM in University of Cambridge. And then onwards, lot of work has been done on electron microscopes by different groups, which I will not discuss. So, that is basically in brief the history of how transmission electron microscopes came up in the scientific community and later on used extensively to probe different kinds of phenomena in material science and engineering. So, let me just now get back into the comparison between optical microscope and the electron microscope. Why there is a need to use electron microscope when optical microscope was already existing? What was the basic reason for that? Then we can understand many other features. We know that any microscope, the most important feature is resolution. Resolution means ability to distinguish objects which are separated by small distance, like the one I discussed few minutes back. If I have 2 points separated by a small distance, whether the machine can resolve these 2 points successfully or not. And this was dealt extensively by Rayleigh, and he discovered, or he gave a formula to correlate the resolution with wavelength and other parameters. So, this formula is given by lambda equal to 0.61, delta is equal to 0.61 lambda divided by mu sin beta, where lambda is the wavelength of radiation, mu is refractive index of the medium, and beta is the half angle of the lens, or the collecting power of the lens. So, therefore, if in extreme case, if we consider mu sin beta to be equal to 1, then the resolution become 0.61 lambda, that is about 60% of the wavelength. And if we consider the normal light which is used in the electron microscope, the normal light has different wavelengths. If we consider the green light, which is a wavelength of about 600 nanometers, 550 nanometers rather, not 600 nanometers. So, the resolution power of the light microscopes is approximately about 300 nanometers. So, therefore, we can write down for optical microscope, we can have resolution power of approximately 300 nanometers. So, we cannot resolve any object whose size is less than 300 nanometers. So, that was the basic need to develop electron microscope, because we know that electrons has a wavelength much lower than the normal light. So, if we consider the wavelength of electron, we know that wavelength of electron depends on the accelerating voltage, and normally the wavelength of electron is given by a formula which can be written like this: lambda equal to write it correctly. Yes. So, wavelength of electron normally can be given by h divided by 2 m0 e v to the power half, or rather we can write down this is equal to lambda 2 m0 e, it's a constant, and v to the power half. So, therefore, h divided by 2 m0 e to the power half v to the power half. So, that means the wavelength of electron is a strong function of the voltage by which it is accelerated. So, if we calculate that wavelength of electron at 200 kilovolts, which is used in normal in transmission electron microscope, so lambda will be approximately 0.0251 nanometers. So, immediately you can see that if the lambda is in electron microscope is given by this, then delta will be less than 1 picometer according to this formula given by this. So, therefore, one can clearly see that it is possible to reach resolution theoretically from 300 nanometers in optical microscopes to less than a picometer in a electron microscope, but normally we do not achieve this resolution because of the problem in the lens. So, if we consider optical versus electron microscope, the transmission electron microscope, there is a huge benefit in terms of the resolution or resolving power of the microscope. By knowing this, one can in fact go on and develop different kinds of microscopes to get understanding of the phenomenon happens in the material science engineering. Let me just show you few of these features. So, this particular slide shows you how the microscope has developed from 1668 by Leeuwenhoek to the 2006 by FEI, a company which has manufactured the highest best possible resolution in a time-series electron microscope. Obviously, Ruska and Knoll's contribution is extremely huge as far as the first microscope is concerned. But from 1932 to 2006, in this about 80 years approximately, microscopes, time-series electron microscope have seen a drastic development. So, we are using the Titan microscope, which is now sold across the whole world by the FEI. One can reach a resolution of order of less than 1 angstrom. As I mentioned that although the theoretically possible resolution in this transmission microscope is 1 picometer, but we can never achieve because of the problem of lenses. So, by correcting different lenses, it is possible to have a resolution of approximately 0.6 angstrom, which is the best possible resolution achieved till today. Now, obviously, one needs to know that in a normal transmission electron microscopes, what are the different things are there as compared to a optical microscope. Let me just go back to the optical microscopes. A optical microscopes consisting of basically 3 things. One is illumination system, that is the light in an optical microscope. You can either have an illumination system coming from down in a biological microscope or an illumination system coming from top in a metallurgical microscopes. So, these provide the source of the light, and then we have to have a sample obviously which is placed on a sample holder, at the top of which we have basically imaging system which is nothing but an objective lens, and from the objective lens the image forms and we can see this on an eyepiece. So, that is basically a viewing or a recording system. Either you can view using a normal eye or you can put a camera. So, this is the basic construction of an optical microscope. We will see that time-series electron microscope looks exactly similar, except that there are a lot of complicated lens system inside a time-series electron microscope, and our source is obviously an electron beam, not an optical light. So, if I describe this in terms of a simple ray diagram, this one look like this shown in the slide. So, you have basically a source here. Source can be electron. We will discuss how the different sources can develop on the electron microscope also. Then from the source, the electron beams are basically focused by a first condenser lens to a very small focused beam, and that focused beam can be again defocused initially by second condenser lens, also can be focused later on in the sample. Normally, in electron microscope we put lot of apertures to select a particular electron beam. So, condenser aperture serves the one of such aperture which can control the beam size. Sample is kept or immersed rather within the objective lens. I already told in the few minutes back how the objective lens is kept in optical microscope. In electron microscope, sample is just placed or immersed within the objective lens, and then these beams which fall on the electron beam which are falling on the sample, some of the beams are diffracted, some of the beams are transmitting to the sample. Those beams can be used to form images by using objective lens, or they can be used to form diffraction patterns by the objective lens. A diffraction pattern normally forms at the back focal plane of the objective lens. So, these diffraction patterns can be either a selected area diffraction pattern, or can be micro diffraction pattern, or can be even convergent electron diffraction pattern, depending on what kind of techniques you are using. And these images or the diffraction pattern can be then magnified using intermediate lenses or the projector lenses. This is in a nutshell a structure of a conventional TEM. So, therefore, it is not as complicated as we think or as we observe or look at it. In one of the lectures, I am going to show you the actual transmission electron microscope and how it operates. But for the sake of understanding today, you can clearly see that if we have a source, electron beam source, we can use it to form an image on a plate. This is mainly because the electrons cannot be seen by eye. So, therefore, once the electron falls on a phosphor screen, then only we can see the image or the diffraction pattern. So, that is kept at the bottom, and that is why a person sits and looks at the screen when the microscope is running as a sample in the column. So, whole thing has to be under vacuum, because electron cannot travel. So, the whole thing is under vacuum. Electron cannot travel in air. So, that is why we need to have very high vacuum system to have a very good microscope, and the samples obviously are to be thin enough so that electrons can pass through it, can diffract it. So, as you can clearly see, as the electron falls on a sample, there are a lot of interaction happening, and so now next thing which I am going to discuss is that how this interaction can be used up. So, let me just go back and tell you how this interaction can be used in the real for different purpose of the transmission electron microscopes. If I considered this to be my sample, and let us assume that electron beam is falling on a sample. This is my incident electron beam. We are going to see how this electron is going to interact with the sample, because this interaction will give us an idea how they can be used for different kinds of analysis. Obviously, for some of the electrons will get absorbed inside this material. They can be called as absorbed electrons. Some of the electrons will pass through. They are known as the transmitted electrons. Some of the electrons which will pass through, they are actually passing, these electrons which are transmitted are passing through without undergoing any kind of deviation from its original path. So, that means these electrons are not undergoing any scattering, but some of the electrons which are passing through may undergo scattering or diffraction. So, these electrons can be of two types, one which undergoes elastic scattering, or we can call that elastically scattered electrons, and other electrons can be inelastically scattered electrons. So, elastically scattered electrons are the ones which undergoes the normal electron diffraction and form the electron diffraction pattern. Inelastic scattering electrons can lead to different kinds of things. Obviously, one who has seen the electron microscopes, who have seen the Kikuchi lines or Kikuchi bands, they actually form because of the inelastic scattering electrons, or we can use it for spectroscopic analysis like in energy loss spectroscopy, which we will discuss later on. Now, if let us look at what happens to electrons which are reflected back or scattered in the direction of the in the other direction, that is opposite to the direction of the incident beam. Some of the electrons will come from the very small thickness of the top surface of the sample. They are called secondary electrons. Some of the electrons, these electrons are actually generated because incident beam electron is having very high energy. So once these electrons fall on the sample, they can eject some of the electrons from the outer cells of the sample, and because of these electrons which ejected from the outer cell of the samples will have low energy, they will just come out from the surface and can be called as a secondary electrons. Some of the electrons which are falling directly from the on the sample may go and hit the nucleus of the atoms, and they can be then backscattered. So they are called as a backscatter electrons. Okay. Not only that, some of the incident electron may even cause ejection of the electrons from the outer cells or the inner cells, outer cells. So some of the incident electrons can actually eject electrons from the inner cells of the atoms in the sample, and once this ejection happens, some of the electrons which is outer cell can jump into the inner cell which has become vacant now, and because of this transition from the outer cell to inner cell, the energy can be released in terms of X-ray. So therefore we can have X-rays coming out because of the interaction with the incident beam and the sample. So in many cases it has been found that auxiliary electrons can also come out from the top surface of the samples. Some of these samples, like semiconductors, they can even produce photoluminescence. So once you know that electrons during interaction with the sample can generate so many different types of signals, we can use each of these signals for different kinds of purposes. The signals which are passing through or rather transmitting and either getting diffracted or not getting diffracted, they can be used basically for the transmission electron microscopes. Okay. X-rays generated by this kind of interaction with the sample can also be used for the transmission electron microscope, which we will discuss when we discuss about the EDS or energy spectroscopy. The electrons which are described as secondary electron as backscatter electron, they are used in SEM for imaging. Auxiliary electrons are used in Auger spectroscopy for getting composition and even to know the state of the electrons. X-rays, as I said, can be used for energy dispersive spectroscopy or EDS analysis both in SEM and in the TEM. And as I said, photoluminescence can also be used for different kinds of semiconductor material analyzing the photoluminescence characteristics. So by knowing that electron can interact with the sample and lead to different kinds of signals, we can now devise the techniques in the electron microscopes, especially in transmission and scanning electron microscopes, to utilize each of these signals and provide the information from the samples which you are probing. So next I am going to tell you how this can be used. So this slide, what has been shown is the basic features, not all the features which I have shown in the board, basic features. So if you see, the incident electron beams falls on the sample, and then we have a direct beam, the beam or the transmitted beam electron which I have written there, which has not undergone any kind of scattering. So that can be used to form what is known as bright field image in TM. On the other hand, elastically scattered electrons, which is shown even on the blackboard, can also be used to form diffraction patterns. Inelastic scattering electrons are normally used in energy loss spectroscopy, electron energy loss spectroscopy, and for the electrons which like backscatter as secondary electron, as I said, they can be used in the scanning electron microscope. X-rays can be both used in the TEM as well as in SEM for energy dispersive spectroscopic analysis to get composition analysis in the sample. So, that is in a nutshell what is basically used. What I have not talked about is that this backscatter electron can also be used to obtain crystallographic information in SEM. There is a new technique which has been developed of late from 1990s known as electrons backscatter diffraction or EBSD, that is used extensively now to get diffraction information and as well as texture studies in the material. So, therefore, we shall discuss in our subsequent lectures the imaging in transmission electron microscope, bright field and also the dark field images as well as diffraction pattern and other contrast mechanisms. We shall discuss about the EDS spectroscopy analysis in one of the lectures. We shall discuss about the EBSD in subsequent lectures. Also, we shall discuss about something related to high resolution microscopy. So, I will also like to tell you one more thing about the electron microscopes, which is known as depth of field before we go into the details of the other features. Depth of field is basically a measure of how an object is in focus at the same time. Like if you have a very object which is very ups and downs, or there are a lot of undulation on the surface of the object, whether can you bring the different portion of the sample or objects in focus or not. As you know, the optical microscope has a very low depth of field. So, therefore, any sample which is very rough cannot be brought in focus in optical microscope very easily. On the other hand, electron microscopes have a very large depth of field. So, therefore, they can be brought in focus in electron microscope very easily. That is why those of you who have already seen the electron microscope or TEM especially have seen that many cases we record the images in a plate and the plates are kept at a distance much lower than the viewing skin. So, if the depth of field is not high, so high we cannot even record these images under the same focusing conditions. Because depth of field is very high, so therefore, we can use both the TEM and the SEM to get good understanding of the surface features of the sample, especially in SEM. So far we have discussed about the different types of signals which can be generated from the sample when electron beam interacts with the sample. Let us now look at seriously each of this in a transmission electron microscope. In transmission electron microscope, electron beams accelerated by about 200 to 300 kilovolts are allowed to fall on the sample. So, therefore, incident beam which is very high intense falls on a thin sample and then interacts with the sample. As I said that during interaction it can either create a scattered electron beam which is elastically scattered or inertially scattered, or it can generate a beam which is not undergone any kind of scattering. So, in a normal transmission electron microscope we can use the forward scatter or the transmitted electron beam for bright field image. This is done by putting a small aperture here. So, once we put an aperture is nothing but a thin plate with a hole. So, we can block all the other radiations except this transmitted electron beam. So, therefore, image formed by this can be easily called as bright field image, because this image will have bright contrast or the image will be brighter contrast. That is why it is called a bright field image. To give an idea how this is done, let us see here. This is taken from a sample which is TiB2 or titanium diboride thinned by to the electron transparency. So, if I see the diffraction pattern obtained from this grain which is shown here, the diffraction pattern will look like this. with a transmitted electron beam here, and that means that this one is formed because of the forward scatter or the electron which has directly passed through without undergoing any kind of diffraction. On the other hand, the electrons which have undergone scattering or diffraction can be seen like this. These are elastically scattered electrons which has led to the diffracted spots. Now, if I put my aperture only on the transmitted beam, that is what I said you, I generate this image at the top left, which is known as bright field image. On the other hand, if I consider one of these electron diffracted beams like this one here 101 and put my aperture around this, and then I form an image, what I get is known as dark field image or the central dark field image. Center dark field image. This is obtained by bringing this weaker reflection on the opposite side, which is same as this one, to the center and put the aperture. If we, instead of bringing this weaker reflection to the center, if we bring this one, the strong reflection 101 to the center, and we can form an image is known as the weak beam dark field image. As you can see in the bright field image, there are a lot of dislocation inside the sample, and these dislocations can be very nicely seen in a weak beam dark field image, or can be easily captured in a weak beam dark field image. The reason is this: in a center dark field image, the whole grain is illuminated strongly because it is diffracting strongly. So, therefore, the defect structure cannot be seen so nicely. On the other hand, in a weak beam dark field image, you can easily reduce the intensities because you are bringing the strong parts in the central position, therefore, intensity will be reduced. So, therefore, you can create a much better image. So, this is in a nutshell in a conventional microscope is done routinely. That means, you can go to a sample, go to a region of the sample which is thin enough, then orient it to a particular crystallographic axis and get the diffraction pattern. Using the diffraction pattern, you can either take a bright field image or a center dark field image or a weak beam image. This is a very routine thing normally people do. But in advanced characterization course like this, we are going to learn how we can see even much better, how that we can see even atoms or column of atoms in electron microscope or not. In fact, with the use of the advent of the new generation electron microscope, we can see very nicely the atoms or columns of atom in a sample. That is what I will tell you now. Okay, let me just get into that. This again is basically to describe you how electron microscope can be judiciously used to obtain a lot of informations, particularly the spectroscopic and the real space information. As I said, a diffraction pattern can be used to generate bright field, dark field, weak beam, weak dark field, and center dark field images. The diffraction pattern is basically tells you the reciprocal space information, as we have already learned from the normal course on characterization techniques. So, the spots are actually related to the reciprocal space. So, therefore, to obtain the atomic structure, how the atoms looks like in a sample, one need to get the real space information. That is where the atoms are sitting in a sample. So, that is what is called real space information. That can be obtained by something known as the phase contrast. So, therefore, the contrast which I discussed here is basically coming from diffraction, and they are known as diffraction contrast. So, they can be changed depending on the diffraction conditions. On the other hand, one can use something known as phase contrast, which we will discuss in detail in the next class. Phase contrast. What is that? Let us now look at first the sample. This is zinc cobalt gallium oxide. It is nothing but a cobalt dope zinc gallium oxide, zinc cobalt and gallium to zinc oxide. And if you look at the diffraction pattern which is shown here, it shows a particular symmetry, and zinc oxide, as you know, is hexagonal crystal structure. Therefore, this diffraction pattern is taken along 0001 of the zinc cobalt gallium oxide, and the crystals are by taking the wide field image, by selecting aperture from the central beam or the forward cutters beam, we can see the crystals of these zinc cobalt gallium oxides are of the size of about approximately 80 to or 60 to 100 nanometers, and they are elongated. So, morphology, shapes and everything can be seen. Some of the crystals are black, some of the crystals are a little less black. So, some of the dark contrast, some of the light contrast. So, this dark contrast, light contrast mainly because of the diffraction. The ones which is undergoing strong diffraction will show the dark contrast, the ones which are not undergoing strong diffraction, they will be showing the light contrast. Now, once if I want to take basically the phase contrast image. So, what you need to do is that you can select a set of spots, okay, like first 6 and along with the transmitted beam, you can select that spots and put a big aperture like that, and then you can form an image which is shown on the right hand side. So, as you know that the transmitted one or the beam which has passed through the sample has not been undergone any kind of diffraction, it is considered. So, therefore, it contains a certain phase of the electrons. On the other hand, the diffracted beams have been undergone diffraction. So, therefore, they contain a phase information. Phase means the electron phase. So, if I select all the beams and allow to interfere them in a normal time electron microscope, I get something known as interference pattern, and interference pattern will show me the columns of the atoms, which is shown here very clearly. You can see the different columns of the atoms sitting on the surface. Not only that, in fact, one can actually take this real space atomic arrangement image and do Fourier transformation in the using a particular different kind of software which are available in the market, and then one can easily get back this diffraction pattern which we have been obtained in a normal electron microscopes. So, therefore, this can be used to prove that whatever image is formed using the phase contrast mechanism is basically reflects the real space informations. On the left bottom corner of this slide, we have shown the EDAX or energy disperses the spectroscopic information. From this, one can see the peaks correspond to cobalt, zinc, gallium, and obviously this one corresponds to oxygen. So, by knowing this, you can see here also oxygen, zinc, gallium, cobalt peaks very easily. So, by knowing all this information, the normal wide field, the spectroscopic information as well as the phase contrast image, you can get lots of information from the time electron microscopes. This is a zoom view. One can really see of this high resolution micro image, one can really see each column of atoms very specifically in a high resolution image. This can be done routinely now in many microscopes, because microscopes capabilities has been increased. As I said, many microscopes have been produced obtained in the market now with a resolution of less than 1 angstrom. So, that is why these are no longer a big problem nowadays. In fact, even a routine user can get this kind of images. This is another one, whereas cadmium sulfide nanocrystal has been imaged. One can even see here the hexagonal arrangement of the atoms very nicely. Cadmium sulfide is basically having hexagonal crystal structure. So, this is a very small crystal, approximately 4 nanometers. Even you can see the atoms at the surface very clearly here at the edges of the sample. It is a very nicely faceted crystal. The advance has happened so much that in the microscopes called Titan, which has the best possible resolution in the world, can even tell you the type of atom present on the sample. If I go back here, I cannot see from this, I cannot tell from this high resolution image whether this is a cadmium atom or this is a sulfide atom. It is very difficult to say the type of atom cadmium or sulfur, very difficult to do a normal electron microscopy. But with the advent of the titan, with the new kinds of contrast mechanism, one can basically tell what kind of atoms are present on the surface by something known as Hardy stem or high angle annular dark field image scanning transmission electron microscopy. This image is taken from germanium crystal, which is oriented along 1, 1, 2 directions. You can even see clearly germanium dumbbell structures on the surface taken from this titan microscope. This is again taken from a zinc sulfide crystals, where cadmium sulfide crystals, where you can see the twin structure. In a summary, I can say that I have discussed today the interaction of the electron beams with the material and how this interaction can be easily used to generate different kinds of images, either diffraction contrast images or a phase contrast images in a transmission electron microscopes. In addition, at the beginning I have discussed to you how the transmission electron microscope has come up from 1925 to 2006 in this about 80-90 years of time period, and also I discussed the resolution, the depth of field, along with different mechanisms of the image formation in the transmission electron microscope. In the next class, first thing I will go is I will take you to a transmission electron microscope and show you the real transmission electron microscopes and demonstrating you how these different techniques can be used for analyzing the samples in a microscope. Okay.